Hi, this is Erin Strong and Josh Becker from UW-Sheboygan, and this is our project about Newton's law of cooling, and we're applying it to winemaking at home. So the introduction, Newton's law of cooling is an application of the laws of thermodynamics, and then basically we're just looking at the rate of change of the object proportional to everything around it. So the room temperature and the cooling constant of the material. So for our project, we're looking at wine.
So the application we looked at was homemade winemaking. One of the first steps in trying to make wine at home is adding yeast to the juice that is made. Adding yeast to the juice will allow the fermentation process to begin, which will turn the juice into an alcoholic juice, aka wine. And for the yeast to begin the fermentation process, the liquid has to be at an optimal temperature, and that optimal temperature is actually a range, so you have to get the temperature of the juice between a range, otherwise the yeast either will remain dormant or it will become too hot and die. So in the ideal making of wine, you want the temperature of the juice to be in the optimal range before you add the yeast. So Newton's law of cooling is used to get the juice up to the optimal range and to keep it at that range. So in our mathematical model, which we can see down here, we have a cooling constant K, the temperature of the juice T, and the temperature of the surroundings Ts. And we also have the transfer function down here. And then our input was the temperature of the surroundings, which is controlled by a different system, which we are not going to talk about in this project, but you can control that. Our output is T, which is the temperature of the juice, and the cooling constant K is going to be different for each system you want to look at. Now we're going to go into the time domain analysis.
Right, so the cooling constant K we used was very small, 0.00025 over 1 second, and the cooling constant K actually depends on the type of juice you use. So for our system, the impulse response was stable. That's because it goes to a constant value after the impulse is applied. And then for the step response, it goes to 1. So it's also stable.
So talking about the stability of the system, the system is stable because lambda, which is the eigenvalues, are in the left half plane, and you can see that from the transfer function. The eigenvalues is where there are zeros, so we get that when s plus k equals 0, and it's going to be the negative value of k, and k will always be a positive value because it's a constant. And then if we look at the Bode plots, this system appears to allow low frequencies through and seems to attenuate higher frequencies as we go up into higher frequencies. And then discussing the unity feedback model, we have a step response and an add block, and then our transfer function, and then the scope, and we get our output down here, which again shows just like our step response, it approaches a constant value and then levels out. And this is consistent because with the feedback it should become stable, and the system already was stable, so we should expect it to remain stable. Thank you for watching.